This is the second part of the lecture about technical adequacy in measurement. Just a quick review. I'm talking with technical adequacy about how confident you can be in accepting the results and the inferences made from the data. In other words, your confidence depends on the technical adequacy of the measurements that are made. So I described validity in part one. That, you'll remember, means that the data measures what the researcher says it measures. So it is technically adequate for making inferences and being confident about the results. In other words, the measurements made are valid to use for answering the research question. Now in this part, I'm going to talk about reliability, which is another piece of the technical adequacy of the measurements. Reliability is basically the same as consistency. It means that every time I use an instrument, I'm going to get roughly the same results if the participants are similar. So if I use an IQ test for 30 10-year-olds, the test is reliable if I get similar results for the 30 10-year-olds in the class next door. Or if I use an IQ test when the children are 10 years old and the same test when they're 11, I would probably get pretty similar results. We know that about IQ tests. They are very reliable. Let me give one of my silly examples. If I want to measure the height of 30 teenagers, I would probably use a tape measure or some kind of meter stick. If I measure each child 3 times, I'm going to get pretty close to the same result for each child. If 2 of you were helping me with meter sticks, we would probably all get really similar results for each child. That method of measuring height is reliable. However, if I decide to measure by estimating or standing back 3 meters and squinting at them with my thumb, I'm very likely to get a different height for each child every time I repeat my measurements. And then if 2 of you were helping me, well, you can imagine how different our results would all be with our thumbs and squinting at them. That is not a reliable method of measuring, or not as reliable as a meter stick would be. And the problem is it's a silly example, but the more important our results are in making some decision or some policy about children's lives, the more critical we should be of the reliability. Reliability means that our measurements don't have error in them. And that is a dream. There will always be a little bit of error because we're dealing with complex human beings. But if you think of the things that affect reliability, you are actually listing possible errors. One source of error is the administration of the test. If we are giving reading CRTs and one teacher tells her students, just guess if you don't know the answer, and another tells his students, leave it blank if you don't know the answer, it should be really obvious that the results are not likely to be similar in both classrooms. So the way that the test was set up, or the children were instructed, actually introduces error into the results, and they are not going to be as reliable. We can try to eliminate some of the sources of error, like inconsistent instructions. We often script them if the test is really important, but it's very difficult to eliminate all factors. Some students may be hungry, sleepy, grouchy, in love with and distracted by the girl sitting 2 rows over. So our reliability is never going to be perfect. There are some characteristics of people that we know affect reliability too. For example, if you're looking at the reliability with very young children on almost any tool, you're not going to get very reliable results compared to older children. Little ones just change too quickly and too much, so fast. In your textbook, Table 8.2 is a really good description of some sources of error, so be sure you look through that and make sure that you understand it. To measure reliability, we actually do come up with a number. We analyze the correlation or the relationships between the tests or the instances of the same tool. This gives us a number, and this is known as the reliability coefficient. So a correlation of 0 means there's absolutely no relationship there. And a correlation of 1, which never which would be the exact duplicate of it. It means there's perfect relationships. It's basically the same thing. So if you're down in the area of 0, the tool is not going to be reliable. It means that there's no relationships there, so there's no consistency and there's no correlation. As you get closer to 1, you're looking at perfect reliability, perfect consistency, and perfect correlation, which never really truly happens. But this reliability coefficient you will find actually addressed in the research that you look at if the person has actually done tests of reliability, which they should. So if you get down into if you were to see a reliability coefficient of 0.3, for example, you couldn't put much confidence in those results. And that can go the other way too. So maybe a researcher found a result, but you're not going to be really sure you can trust it or generalize it with a reliability coefficient of 0.3. But on the other hand, maybe the researcher reports that he or she found nothing with a reliability coefficient of 0.3. Well, you wouldn't have too much confidence in your interpretation that there's nothing there, because there could be, and it was missed. If the measurement wasn't reliably measuring what the person said it was measuring, yes, they could have missed, and missed it by a long shot. So I've given you some rules of thumb there. If the reliability coefficient is less than about 0.6, you need to be really cautious reading that. That's not very good. And if it gets up into 0.8, then there's room to celebrate there. That would be terrific. And that's the sort of, and even above 0.8 is what we shoot for with some of these tests that are around and have been used for years and years and years and edited and fixed and revised over the years. Now, there are different types of reliability or different things you look at to build these correlations or to find these correlations and come up with a number. The first type of reliability is called stability, or more commonly you'll hear it called test-retest. And when we run those numbers, we take the same people and the same tool and we measure it twice. You have high test-retest reliability if the results are similar both times that people take it. The first limitation for this is obvious. If you're going to administer the same assessment twice, people are going to remember it, and this is called a carryover effect. We can use some statistical controls for it, and sometimes we even toss in a distractor activity or two so that the two tests are seen as different by the subjects. And another thing that helps is if we use a sensible amount of time in between the two tests so that at least they forget a little bit of it in between. The second limitation is simply based on human characteristics. There are some traits we have that are not stable from time to time. So giving me a test of my mood on one day and then 2 weeks later using the same tool to test or measure my mood again is obviously that's not the appropriate way to test the reliability of that tool. Obviously, each person's mood is very likely to change from the first testing occasion to the second. So you really have to understand the trait you are trying to measure and its relative stability over time if you're going to come up with the reliability coefficient this way. Another type of reliability, of way to come up with this reliability coefficient, is to use equivalent or parallel forms of the test. And this means that you give it to the same people at the same time. So basically, they're taking two tests. Imagine that you've created a new math problem-solving instrument. You can give a group of people a test for which the reliability's already been established, and you can give them questions that are from your new test. If your new test is reliable, it should produce similar results. And this is often how newer, better instruments get created by comparing them to older instruments. It is, however, very surprisingly difficult to do this. It's really, really hard to create two instruments that are roughly the same. In addition, the length of time for testing your participants could be a real problem. They could end up falling asleep on you. You will often see this in educational research, though. Those of you in the classrooms are probably kind of familiar with state CRTs. There are always multiple forms of those tests. So the children in the room are taking different forms of the test at the same time. It takes a huge pool of items, test items, to be able to do this. And item pools are labor intensive to develop. You have to put together panels of writers, and then reviewers have to edit them and check them. If you've heard of field testing, that when scores don't usually get reported to the people because it's a test of the test, and one of the things they are testing is the reliability of that. One of the things they're doing is testing the reliability of the different forms of the test, and then they're throwing out questions that don't fit, that don't, to narrow down the pool of questions until you get this really wonderfully reliable pool of questions. You can actually mix together equivalence, reliability, and stability, or test retest. And you could take the same people for two different tests on two different occasions. And this actually helps with the carryover effect. So they don't, oh, I saw this test 2 weeks ago. This is silly. But it's still very, very difficult to create parallel forms. And you still have to be cognizant of the traits that are not stable over time and make sure that you're not, then you've got a validity problem because you're not really using the right tool to measure those. Another way of coming up with that reliability coefficient is called internal consistency or reliability. And here we want to see a really strong correlation or relationship between items that are similar. So items measuring the same thing should hang together. So you give subjects one test, but every question on that test has a parallel question. You might even have noticed this on some surveys you've taken. You read the question and you think, didn't they just ask that? Or didn't they just ask that the opposite way? And they did. They are trying to see if both questions are answered the same way, and therefore the questions are the test is reliable and it's measuring what you need it to. You need a lot of questions if you're basically going to compare two halves of your test. So a minimum of 10 questions, and that would be really, really light. And then you have to be careful because your subjects could get really irritated. So they need to be able to help you out there. When a researcher is reporting internal consistency, he's going to use some ways to give you that reliability coefficient, and you will see these in reports. You don't need to know how these are run, but I want you to be familiar with the terms so that they kind of jump out at you and you realize that the person is measuring reliability. The Cooter-Richardson is not all that common because it's really only useful if the test has multiple choice with right or wrong answers. There's obviously wrong answers and there's a right answer, or a yes, no, or a true, false kind of test. But you'll see it reported as the Cooter-Richardson reliability, or KR sometimes. More common is Cronbach's alpha, and sometimes it's just simply called alpha. And you will see this a lot in the research. And it's reporting the similarity of results from similar questions. So you need at least 3 items in the scale, and it's that relationships between the questions that are asking the same sort of thing. So look for the alpha. That's very, very common in it, and a way of reporting the reliability. When there's really no way to use any of the previous types of reliability measurements, you can measure agreement at least. Usually you're looking in these cases at how consistent different raters or observers are. I did a study once in which 2 of us were categorizing elements of lessons that were published. And so I had to actually run a correlation between my ratings and my research partners to show that we were doing roughly the same thing. We started out the study before we started actually gathering data. We spent a long time comparing notes and arguing about our categorization until we could get to the point of about a 0.8 inter-rater reliability, which is really good. And then we started our data collection. So it was done prior to that. And there, when you do that, you're going to see Cohen's kappa. And that is talking about this rater agreement in rating different things that are being judged. So the importance of reliability is that it leads us to trust the results because we know that the tool is consistently measuring this construct that we want to measure. It's always established before the research. If you need to report the reliability of an instrument you've developed, you need to do pilot studies. There need to be expert panels have looked at it, and there should be field testing if it's going to matter a lot to some decision that's being made. Think back to my silly example of measuring height or estimating height. If you're going to trust my results, or they matter to some kind of decision you're making, you want me to use the most reliable measurements I can of height. Think now about the relationship between validity and reliability. I can measure the wrong thing, but measure it very consistently. This means that I could have a very low judgment of validity for my measuring because it's not measuring the right thing, but it could be highly reliable. For example, we can get a measure of taxable yearly income on a group of people. That would be very, very reliable. But if I then try to use those income data to represent intelligence of those people, I'm not making a valid measurement of intelligence. It's not a valid use of those data, even though those measurements were very reliable. Even more silly, I can consistently and reliably measure the circumference of your head. But it would be absurd to use those measurements to represent how smart you are, unless we want to go back to the early 1800s and start all over again. You cannot have valid measurements if they are not reliable. Let me repeat that. The measurements are never valid if you can't even show that they're reliable. They need to be reliable before you even make a judgment about the validity. If I'm trying to measure intelligence, but it's different every time I measure it, the instrument is not reliable. So there's no valid way to say I'm talking about intelligence. But just because a tool is reliable does not mean it's a valid way to measure. I could measure the wrong thing very well, and I could measure it very consistently. So to wrap up, validity is about the appropriateness of the tool. Is the tool appropriate for measuring what I say I'm measuring? Reliability is about the consistency of the measurements in that tool. Is the tool consistent in measuring? When we are talking then about the technical adequacy of data collection, we're talking about the validity and reliability of how the tool is being used. And these are what we call psychometric properties. If we're going to be really erudite, we could say that we are addressing the technical adequacy of the data collection through the psychometric properties of validity and reliability.